Today we're going to talk about singularity analysis. This is one of the crown jewels of analytic combinatorics. It's a general approach that really gives confidence that we can handle a broad variety of the generating function equations that arise from the symbolic method. We're well into complex asymptotics, and we're talking about methods that can handle generating functions that are not meromorphic. Now, I have to give a warning here that we're starting to enter deep water in terms of the mathematical sophistication required for these results. We went from the symbolic method to rational asymptotics, which is really not much more than partial fractions. And then we looked at meromorphic asymptotics, which requires complex analysis and residues. And now we're going to look at singularity analysis. But again, even though we're getting into deep water, I promise as at the end of the lecture on meromorphic asymptotics, that our end result is a set of very broadly applicable schema that are really not all that difficult to apply to a big fraction of the kinds of generating function equations that arise. So the end results really are not necessarily all that complicated, but in order to prove these results to be valid, sometimes there's some technical skill needed. So what we're going to do in this lecture is give an overview of the approach, and then we're going to discuss several basic and broadly applicable transfer theorems. And again, full details are in the book, but this introduction, I think, will persuade people that there's a basis for this kind of analysis getting us to good asymptotic results in many, many cases. Now, I'm going to start with a prelude that will help put the characterization of the kinds of functions that we're talking about into context. Now again, the general form of combinatorial generating functions is that we're always going to have an exponential growth factor and some sub-exponential factor. And our first principle is that the location of the singularities are going to dictate the exponential growth, and the nature of the singularities are going to dictate the sub-exponential factor. Now, in the past two lectures, we looked at meromorphic functions or rational functions and saw that the smallest real root of the denominator gives the exponential growth factor, and then if it's a pole of order m, then the sub-exponential factor is proportional to n to the m minus 1. In this lecture, we're going to talk about singularities that are not poles. I have to talk about what I mean by that and then how that impacts the sub-exponential factor. So what it means is not poles. If you go back and look at the definition of an analytic function or a meromorphic function, it's one that can be expanded except for a finite number of poles. And in the end, what it means is that if you can't multiply by 1 minus az to the m and get something that's analytic. And you can go back and look at the series representation to try to check that. And we'll look right now at such a function. And the first idea is, well, how do we extend the square root function to the complex plane? So that one thing you can do is use polar coordinates and write a complex number z as re to the I theta, or cosine theta plus I sine theta. And then you might as well define square root of z to be square root of r times e to the I theta over 2. And that seems to make sense because if you square the square root of z, then you get r, e to the I theta over 2 squared is just e to the I theta, you get z back. So that seems like a good definition of the square root in the complex plane. But there's a problem called the multiple values problem, and that is that there's actually infinitely many values of z for which square root of z squared equals z, because if you take add an integer multiple of pi I to r square root of r e to the I theta over 2, and then you square that, then you get an extra factor of e to the 2 pi I, which is 1. So for any integer k, we've got a number that if you square it gives us back r e to the I theta. So that's the so-called multiple values problem. So what we do is we want to have just one value that if you square gives the z back. So we just restrict theta to be in the range minus pi to pi. So that's the standard definition of the complex square root. It's square root of r e to the I theta over 2, where theta is between minus pi and pi. And there's only one value for every z in that range that if you square it gives back z. So now square root of z is uniquely defined, and square root of z squared is equal to z, so that's good. And this gives us a basis now, say, for writing code to compute the square root. This is straightforward code to go ahead and compute the square root. And it uses, so there's a function that gives the absolute value of a complex number. And remember, these are methods in our complex data type that have the real and imaginary part. So Java's math.hypot function returns the square root of square of its 2 arguments, which is exactly what we want for the absolute value of the complex number. And to get the angle, it's the arctangent, math.atan2, and that gives the angle between minus pi and pi, just what we want, it turns out. So to compute the square root, we take the square root of the absolute value of our number, and then we take the angle and divide by 2. And then convert those over to x plus iy in the standard way, and then return a complex with those values. So that's simple code to compute the square root. And so now we can add square root to our plots, for example. So the question is, does this square root function have singularities? And if we look at our typical plot of the magnitude of square root of z, it seems fine. It seems very smooth. But actually, that's misleading. Actually, there's singularities, but they don't show up on this plot. And also, they're not poles. They're not isolated. So we'll see what that looks like on the next slide. So the reason that there's singularities shows up if we plot the angle or the argument. There's a discontinuity in the argument on the negative real axis. And that has to do with this restriction of theta to minus pi and pi. So here's just an example of how we can show there's a discontinuity. So let's take 2 points, one just above the negative real axis and the other one just below the negative real axis. So now, by the definition, if we take the square root of those 2 points, the key thing is that this one down here, well, so let's do the first one, the square root of z plus. So that's at pi over 2 minus a little bit. And so the square root of that is going to be e to the I pi over 2 minus a little bit. But the other one, it's not pi over 2 plus a little bit because that's not in the right range. It's actually minus pi over 2 plus a little bit. And what that means is that if you take these things arbitrarily close, epsilon arbitrarily small, these things come arbitrarily close, but their arguments differ by I pi. So that means that they don't get close together. The functions don't get close together when the values get close together. And if you go back and look at the definition of differentiability, that means that it's not going to be differentiable. And not differentiable means it's not analytic. It means it's a singularity. And the thing is that it works for any z on the negative real line. It's not differentiable And there's an infinite number of points there all clustered together. So they're not isolated. A pole is something that's isolated. We're going to multiply by 1 minus z times the order of the pole and get rid of it. With these, you can't do that. There'll always be another one right next to it. So that's called an essential singularity, and complex square root function has an infinite number of essential singularities. That's the key to understanding that we're going to need different methods than we use for meromorphic function, where we're just working with power series and isolated poles. So that's an example of essential singularities, and it's a key example and worth studying. And the other thing is that wherever you use square root, this is going to show up. So this is square root of 1 minus 4z, so you're going to have an infinite number of essential singularities on some line. Okay, what about logarithm? That's another fine example, and actually these two examples are the critical ones. We can do the same sort of thing. If we have z equals r e to the I theta, we can define log of z equals log r plus I theta. And that seems to be good, because if you take e to the log z, then you get r e to the I theta, you get z back, which seems to be what we'd want. But you still have the multiple values problem, because you can, again, add a multiple of 2 pi I and still have e to the that number equals z. So again, we want to define log z where theta is restricted to be in the interval from minus pi to pi. And that again gives us a definition of the log function such that log z is uniquely defined and e to the log z equals z, which is what we want. And again, this leads to simple code to get the log. It's just a two-liner. Just take the log of the absolute value and then use the same angle as the imaginary part. That's what we can use to do plots. With log, there's other problems, not just the singularity problem, which I'll talk about on the next slide, but there's things that you might expect should hold true, but they only hold true when the angle's in the right range. Like log of e to the z is equal to z only when the theta's in the right range. Or you can't even do things like log of wz equals log w plus log z unless the angle's in the right range. So the more restrictive things what you do with calculating with the log function. But again, in the present context, the question is, what about singularities? And again, if you plot the magnitude, it looks pretty smooth like other things that we've seen. But if you do the angle, the plot of the argument, you get the same kind of problem. And I'll skip that argument because it's very similar to the square root example. There's a discontinuity on a negative real line actually starting at 1. And again, so it works for any z less than 1 in the real line. And so the log function also has an infinite number of essential singularities. They're not isolated, and they have to be dealt with differently than poles, which we can just work with polynomials and power series for meromorphic functions. And again, if you have any time you use the log, you're going to run into this problem. That's the complex logarithm. So those are two functions that play a key role in trying to deal with generating functions equations that are not meromorphic. And usually they're not meromorphic because they involve one of these two functions. Now there's another famous function on the complex plane called the gamma function. And we could spend a whole lecture or a whole course on the gamma function, so I'll just quickly summarize it on this slide. And it comes from the idea of trying to extend the factorial function to the complex plane. So Euler, in the 18th century, came up with an integral representation that works on the reals and actually continues to the whole complex plane except for the negative integers. So that's an integral representation, and think of S as real just for a moment. Integral from 0 to infinity, e to the minus t to the s minus 1 ds. So why does that work? Why does that extend the factorial function to the, say, non-integral reals? Use integration by parts to get the key identity. Well, first of all, if you take gamma of 1, that's just 1. It's e to the minus t from 0 to infinity. It's just 1. But if you do integration by parts, then it's very easy to show that gamma of s plus 1 equals s times gamma of s. And so that means then from those two things you can prove that if the argument is an integer, gamma of n plus 1, where n's a non-negative integer, is equal to n factorial. So it matches n factorial on the integers. That's clearly what we want, but it's defined for all reals. So that's the key idea behind the gamma function. So like, for example, a very important value of the gamma function is gamma of 1/2, which is e to the minus t over square root of t dt, which by change of variable is e to the minus x squared dx. And that's a well-known definite integral related to normal distribution is the square root of pi. Gamma of 1/2 is the square root of pi. And that's a key fact that actually plays a very important role in this lecture and in the asymptotic analysis of many, many combinatorial classes. Gamma of 1/2 is square root of pi. Once you have gamma of 1/2 being square root of pi, then you can use the gamma of s plus 1 equals s gamma of s to get gamma of other values like minus 1/2 or 3/2. That's a very simple computation using gamma of s plus 1 equals s gamma of s. And some of these values will come up in this lecture as well, but so far this is pretty elementary real analysis that shows this. Now, but there's way more to the gamma function, as I said, in a couple of forms of the gamma function, which I'll present without proof, but was known to mathematicians centuries ago. One famous one is the Weierstrass form. 1 over gamma of s equals se to the small gamma of s, and small gamma is Euler's constant. That's the same constant that comes up in the asymptotic approximation of the harmonic numbers, times product for n from 1 to infinity of 1 plus s over n times e to the minus s over n. That's the Weierstrass form of the gamma function. Again, centuries ago, mathematicians worked with these product forms of many functions. Another famous one due to Euler is for sine of s equals product from 1 to infinity 1 minus s squared over pi squared n squared. And these forms were interesting to these mathematicians at this time because they actually give a good way to compute these values. Because as n gets bigger, these things get closer to 1, so you can get approximations to them. And then actually we're going to use it that way. But anyway, we'll state those without proof for now. And so then you can do things from these forms, like prove that gamma of s times gamma of minus s equals s pi over s sine pi of s. Kind of amazing kind of identities that you wouldn't think there'd be such a relationship, but boom, there it is. Or another famous one is so-called reflection formula, gamma of s times gamma of 1 minus s equals pi over sine of pi s. Those derive pretty easily from the product forms. Amazing identities, and they play an essential role in all kinds of applied mathematics. So again, I don't have time in this lecture to do much more than just state them, but they do play a key role in singularity analysis. In particular, there's a representation of the gamma function known as the Hankel representation. And what that one says is it has to do with complex integration. And it says that 1 over gamma of s is 1 over 2 pi I, an integral around this contour that circles around the positive real axis and then circles around the origin and then goes back out infinite, of minus t to the minus s e to the minus t dt. It's a Hankel representation of the gamma function. And that looks a little strange, but actually, given the product forms, it's actually not hard to prove because what you can do is just take the two lines and it comes out to be e to the I pi s minus e to the minus I pi s over 2 pi I times that integral. And that integral is gamma of 1 minus s, and the other one, that's the definition of sine pi s over pi. And so from the reflection formula, you get back 1 over gamma of s. Now, it's not my point to prove all of these things, but this is a key formula that we use in singularity analysis, so that's why I pointed out. And this is all classical analysis, and again, with many, many applications in applied mathematics. So the Hankel representation, the basic identities, and the values of gamma of 1/2, those are the ones that you're going to want to know. That's the basic properties of the square root function, the log function, and the gamma function in the complex plane. And that's a prelude to what we're going to need to know. What about singularities of the gamma function? Well, we can use that Weierstrass representation to just compute gamma function, and we can then develop a plot. And that's the plot of gamma of z, and from the plot it's clear that there's singularities and there's other ways to show it. So actually a gamma function has simple poles at the non-positive integers. So with all those basic properties now, we're prepared to start to take a look at singularity analysis. That's a prelude, the square root, log, and gamma functions.